So in this video, we're going to learn the basics of Laplace transform. So Laplace transform is basically when you convert a system that is in the t domain into an s domain, and by doing so, you can solve a differential equation, for example, much easier in the s domain, and then you do inverse Laplace transform, bring it back to the t domain, and you've got your answer. So rather than just solving something in the t domain, which is a little harder, you convert it to s, solve it there, and then you bring it back to your t domain. So this is the first episode in a series of Laplace transform basics. This is part 1 to this unit, and it'll be particularly helpful for those doing signals and systems in their electronics engineering, probably in your second year. So let's start. So theory-wise, I would suggest you read a book like Nagarkani, this one. It's called Signals and Systems. You could read that for theory. I will just show you how to solve it. So the first thing we're going to do is finding the Laplace transform and finding the region of convergence of the Laplace transform. So we're going to find the ROC of a Laplace transform. So the formula for a Laplace transform is integral negative infinity to infinity x of t e raised to minus st dt. So this is what we call a bilateral Laplace transform. If it was from 0 to infinity, it would be unilateral. Anyways, moving on, we want to find the ROC for a Laplace transform. So we have actually 3 types of ROCs. The first one is the right-sided signal. We have the left-sided signals, and then we have the double-sided signals. So I'm going to start with the right-sided signals. So while we do this, I'm just going to do this with an example, and in the example you will see how to solve the Laplace. It's simple integration, and then how to find the ROC. Okay, so step 1, let's just take an example, right? So let me get into it. Okay, so the example is x of t is equal to a into u of t. So as we know, u of t is a step signal which looks a bit like this. And this will be 1. This is a step signal, or your u of t. So we want to find, this is how you write it, okay? One second, let us focus. Okay, so Laplace of x of t is equal to integral negative infinity to infinity x of t into e raised to minus st dt. Remember this, it's very important. And now just put your x of t in here, which is my x of t, that's that. So I have integral negative infinity to infinity, and I can write a into u of t into e raised to minus st dt. Now here's where we start to really solve it. Because we know u of t is a step signal, and a step signal has a value of 1 only from 0 onwards. That means our limits would be 0 to infinity if I were to take u of t equal to 1. Because u of t, or a step signal, only has a value after 0, and the value will always be 1. So I can take u of t is equal to 1 and change my integral sign from 0 to infinity, because only in this area do I have a value for u of t. Everywhere else it is 0, and hence if I put any other limit, this would become 0 and my answer would be 0. So I'm going to keep this 1 by making sure my limits are 0 to infinity. So 0 to infinity into a into 1, because my u of t is now 1 from 0 to infinity, and e raised to minus st dt. Here onwards, you solve it like a regular integration. I will not be explaining that. I will just solve it. Okay, so we can stop here. I know you're in the, so when you reach e raised to negative infinity s, I know you're thinking that e raised to negative infinity would be 0. But when we solve Laplace transform, we do not consider that to be 0 immediately. There's one step we have to do before, and I'll show you what that step is. So basically, our s is actually equal to sigma plus j omega. And we replace our s only in the numerator. So this is the denominator s. We don't touch that. We only replace s in the numerator. So we have done a regular integration from this point, and we stopped till we've reached here, till we have just s's here. And we're going to replace our s with this, and you'll see why in a second. So I have a raised to minus s. And now I'm going to put this up there. So it's e raised to negative infinity sigma plus j omega minus 1. And we can actually separate this. So if you multiply infinity inside the bracket, you get minus sigma infinity minus j omega infinity, and that can actually just be multiplied. So I'll show you how. A upon minus s e raised to minus infinity into sigma multiplied by e raised to minus infinity j omega minus 1. Okay, this is a simple property that we know when it comes to exponents. That is, your e raised to a into e raised to b would be e raised to a plus b. So that property is what we use over here. We just multiply it inside, so we get this term plus this term, and we write it like this. Why we do this is because we're going to concentrate on only this one value, that's your sigma. So for sigma and greater than 0 and sigma less than 0, we have two cases here. So if my sigma was greater than 0, then e raised to negative infinity into 0 into sigma would be. So with sigma being a positive integer or a positive number, positive into negative would be negative. So if my sigma was greater than 0, e raised to negative infinity into a positive number would give me e raised to negative infinity, which is 0. If it was less than 0, then this would be negative, right? Because that's what, it's less than 0. Negative into negative would give me a positive value. So e raised to negative infinity into sigma, considering here in this case sigma is negative. Negative into negative will give me e raised to infinity, which is infinity. So as you can see, we need this case. And the only reason we do it this way, I know we can just directly solve it from here by putting this as 0. We have to do this step because we want to find the region of convergence, which this will make it easy. So the region of convergence you're going to find is with this number. And we find this number because of the s in the denominator. So if you had something like s 4 minus s, then you want s to be lesser than 4 or greater than 4, and that's how we would solve it. So, but there's nothing here, there's no other constant that it's plus or minus to it. This can go up, that's why we're not considering the minus. So s can be greater than 0 or less than 0, because we don't want this to be infinity. We want it to end up as a 0 right here, so it makes our answering much easier. So now all you do is you just replace this value up here, your sigma greater than 0, in your this equation. So I would get a upon minus s, and taking this entire thing, in this case I would get e raised to minus infinity. Sigma is 0, so this would become 0, hence this entire term would be 0, and 0 minus 1 is minus 1. So my answer is, minus and minus can get cancelled, is just a upon s. This is my Laplace transform. And my ROC, and this is super easy to find, as I told you, it's just here. So depending on which case is giving you 0, that is the case we're going to mark. So if my sigma is greater than 0, then everything greater than 0 is my region of convergence. Yes. And this is called a right-sided signal, because you see the region of convergence is only on the right side. Left-sided signal will have only on the left side, and both sides will have on either both sides or within both sides. So yes, we will see. I just wanted to add that if you can solve this, you can solve left-sided signal the same way. You would just find that rather than getting this value as 0, your case would be sigma less than 0 is what would give you a 0, and then you would realize that it comes on the side. That's it. I will show you now a double-sided signal because that's just a slight bit different. Left-sided signal you can probably get from just looking at this. I will pause here if you want to just maybe view this entire thing. All right.